A derangement is a permutation of the elements of a set such that no element appears in its original position. Let's think about this with two items, right? Let's say you have two boxes, and this box is for a key, and this box is for a marble. And when you first look at this, well, let's say you have the key in the key box and the marble in the marble box. Well, that makes sense. That's just like right. So what would be a derangement of that is the marble in the key box and the key in the marble box. That would be a derangement. There's a classic problem in regards to this, and we're going to think about derangements through that classic problem. So I have a description of the problem here. I'm just gonna bring it up, and I'm going to read through it. This is straight from Wikipedia. N guests, this is the hat check problem. N guests are invited to a party, and at the door, the guests all check their hats with the butler, who in turn places the hats into N boxes, each labeled with the name of one guest. But the butler has not asked the identities of the guests, and so he puts the hats into boxes selected at random. The problem is to find the probability that none of the hats gets put into the right box. Okay, so let's start with just one guest. We can clearly state that the probability is simply 0, that we don't place that hat into its correct box, right? So let's say this is guest A. A hands off his hat, and there's an A box. There's only one box, right? So there's only one hat, one box. There's a 0.0 probability that we will derange A. It's just not possible. If we think about two guests, let's think about A and B, then it makes sense that there would be a 50-50 chance that we put the hats into boxes that aren't theirs. And we already showed that with the key in the marble issue, right? We've got an A box and a B box, and we're going to, we either put A in the A box or we put A into the B box. And there's a 50-50 chance that we'll get it wrong. So what about when we get to 3 guests? This is where I think it gets a little more interesting, okay? So let's think about 3 guests, and we'll call them A, B, and C. And we're going to think about A, B, and C boxes as well. Okay. So we've got the A box, right? The B box, and the C box. Okay. Now, I'm going to go ahead and count all the permutations. And I'm going to use a reductive counting approach for base 3 here, right? Where we've our base 3 numbering system is this A, B, C, right? Those are our numbers, our digits, you could say. This is going to seem a little bit cumbersome, but let's do it anyway. I like to take these opportunities to show counting as a basis for understanding probability, although we could just use swapping as a means to find permutations here as well. And that's just as valid and computationally a little bit better. So I'm going to count these out. And this is going to take up a little bit of space, so why don't I do it like this? We're going to say, start counting over here. Let's do A, B, A, B, C, A, B, A, B, B, A, B, C, A, C, A, C, B, ACC, BAA, BAB, BAC, BBA, BBB, BBC, BCA, BCB, BCC, C, CAA, CAB, CAC, CBA, CBB, CBC, CCA, CCB, CCC. So let's count these. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, so there's 27 of these. It shouldn't be a surprise that that is 3 to the third power. There's 3 places, there's 3 digits, or 3 numbers, and 3 to the third power indeed equals 27. Okay, so now that that's all counted out, let's cross out the items that don't have duplicated values, and then we'll be looking at the permutations, okay? So anything with a duplicated value, I'm going to cross out, and I'm going to circle anything that doesn't have a duplicated value. So AAA, AAB, AAC, ABA, ABB. Okay, well, there is a value that works, ABC, and then ACA, ACB, ACC, BAA, BAB, BAC is a valid permutation. BBA, BBB, BBC, BCA. Oh, BCA is a good one. Let's get that. BCA, BCB, BCC, CAA, CAB, CAC, CBA, CBB, CB. Oh, I messed up. It's easy to mess up. There we go. CBA and CBB, CBC, CCA, CCB, CCC. Oh, I must be missing one. ACB. Okay. All right. This is a this is sort of a cumbersome approach, but we do have an exhaustive means of doing this, and that's what I'm trying to demonstrate here. So out of these permutations, let's think of what is and is not potentially a derangement, and we'll do that by, we've got an A box, a B box, and a C box. And we're looking at, we're looking at A, B, C. We're looking at A, C, B. We're looking at B, A, C. We're looking at B, C, A, C, A, B, and C, B, A, right? And I'll just draw little boxes around these really quick. So let's cross out the ones that are not derangements, right? And what makes it not a derangement is that it's in the box it's supposed to be. So that one's out. That one's out. Okay, let's look down through the B's. That one's out. Let's look down through the C's. That one's out. So our derangements are BCA and CAB. Okay. So hopefully that gives a solid idea of what a derangement is. We can see that we have 2 derangements, and the probability that none of the hats gets put into the correct place is obvious here, right? If we consider this as our space and these 2 as our subspace, then we have, 2 out of 6 or 1 out of 3, right? So there's a 1/3 chance that we're going to have a derangement. So forgive me, I'm going to be a little hand-wavy now and describe the probability of one derangement. So why don't I do that? I'm going to describe the probability of one derangement as being 1 minus 1 over 1 factorial. And, 1 factorial is 1, 1 over 1 is 1, 1 minus 1 over 1 is 0. And remember, we described the probability of the derangement of one item as being 0. So I'm going to expand this series just a little bit, and let's think about two derangements, right? So this first one is the probability of one derangement, and we'll talk about this next one as the probability of two derangements. This is going to be 2 minus 1 over 1 factorial plus 1 over 2 factorial. And I say, okay, I'm going to back that up a little bit. The probability of two derangements as being 1 minus 1 over 1 factorial plus 1 over 2 factorial. And 1 minus 1 over 1 factorial, of course, is 0. 1 over 2 factorial, well, 2 times 1 is 2. 1 over 2 is 0.5. And we demonstrated that as well. So the probability of three derangements I'm going to describe as 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial. Okay. So, just to point these out, we are swapping our operations here. And you might want to think about why that is. But for now, let's continue to be a little hand-wavy about this. So, right, 1 minus 1 factorial is 0. Then we've got 0.5 here, right, or 1/2, minus 1 over 6. And that equals 1/3. Okay. 1/2 minus 1 over 6 equals 1/3. All right. So you can probably see an emerging pattern here. And this is, in fact, alluding to a more general derangements formula, where we continue this idea out as a procedure for n derangements. So what that looks like is like P sub n equals 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, and so on, right? So you can see that we're increasing if we increase the value of n, we're just going to continue doing this in this direction. Let's write some Python for this and get a sense of what's going on here. So from math, and I'll just do this at the top of the file, I'm going to import e. I already did that, right? I'm also going to import factorial. Normally, I would probably write a factorial function really quick, but that's okay. I'm just going to import it this time. I'm going to define the probability of n derangements, okay? And I'm going to say if n is 1, well, we know that that's 0. So I'll just say 0.0. And then we're going to set an accumulator. And I'm going to set that accumulator to 1. And that's based on this right here, right? This we're starting at 1. And I'm going to write a procedure that's going to take us from the left of this this probability of n derangements moving to the right, okay? So with that accumulator set, I'm going to say for the number in range 1 to n plus 1, if the number is odd, so if num modulo 2 is 1, the accumulator is going to be reduced by 1 over the factorial of the number. And that's exactly what we're seeing here, right? This is odd, so we reduce by it. This is even, so we increase by it, right? So that's what we're seeing, and we can easily reflect that in code. So if num modulo 2 is 1, then we reduce by 1 over factorial of the number. Otherwise, we increase by 1 over the factorial of the number. Okay. And at the end of all that, we can return the accumulator. And that seems pretty good. Now, we've been writing dictionaries, and I'm not going to stop doing that right now. So I'm going to define another function called the Derangements dictionary. And we'll go to n high. All right. So n high, of course, is just we're going to populate a dictionary where we start where the key is the number of derangements, and the probability is going to be the value for that number of derangements. Okay, so define a dictionary, say for n in range. We're going to go to n high plus 1. D sub n is going to get the probability of derangements of n. Okay, and then we'll return the dictionary. I'm going to say for n and the probability in the derangements dictionary, and let's do up to 500. And we'll print n and the probability of n derangements. Okay. Oh. Dot items, I always forget that. Okay. Here we can see something similar to what we saw before. It turns out that as n approaches infinity, the probability of n derangements, or the probability of n derangements approaches 1 over e. That's again what we're seeing here. That's if I were to divide this into 1, we would see very clearly that that's what we're getting. Okay. I'm not going to do that. Feel free to do that, of course. But I'm going to, again, perform a little bit of hand waving. And I'm going to construct E as a simpler summation of values through a related formulation. Okay. So instead of the derangements formula, again, I'm going to reframe this with a little hand waving and construct E as a simpler summation of values through this formulation. E, and this is going to be equivalent, roughly equivalent. E is going to be the summation from n equals 0 up to infinity of 1 over n factorial. So this, if we were to change this to 1 over e, we would get we could construct the derangements, the probability of n derangements formula. And to be clear, what we're describing here, if you're not familiar with this notation, this is simply going to be E is 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, 1 over 3, right, factorial, and so on forever to infinity, right? That is a definition for E. Notice that the values we add in as we move to the right in each pass of this summation are less and less, right? Again, this is simple enough to pack into a dictionary, and we can watch our progression toward E using Python. So let's do that. Move this over here. So I'll say sum 1 over n factorial. I'm just reflecting the operation here, the procedure that we're seeing there. And I'm going to say we'll start our accumulator at 0.0. And I'll say for num in range, and we'll go to n plus 1. the accumulator is going to collect factorial of n, and we can just return the accumulator. And I'll write a dictionary function to pack these in. So 1 over n dictionary, we're going to go up to n max, and we'll define a dictionary, and then say for n in range, and we're going to include n max, so n max plus 1, and we'll say d sub n. It's going to get the sum of 1 over n factorial of n, and we can return that dictionary. Okay. And again, we can just traverse one of these dictionaries and see our output. So for n and the approximate e in 1 over n dictionary, and let's just do 500 again. 500 dot items. I always forget that method, and then I get an error, but I am not forgetting it this time because I'm being very intentional. So there's our n, and here's our approximate e. Okay, so let's print that, and let's also print e. Okay. Oh, what is going on there? The factorial of n for num. Factorial of num. That is much better. All right, easy mistake to make. N and num. I just crossed those over. Okay, there we go. All right. It turns out that by the time we get to 499 and 500, 1 over 500 factorial for our computer is as close to 0 as we can get, and we're not actually seeing a difference between these two. That's okay. But notice how close we actually get. We get the same level of precision. I didn't even realize that. We are getting a level of precision that is equivalent, unless I'm misseeing anything here. No? That's pretty cool, right? That's something that we can do. And we can build a calculation of E very directly. And I think this is also a very common way for us to think about E. Okay. Yeah. And in the next video, we'll look at yet another way of estimating E through Monte Carlo simulation.